This video is going to look at stoichiometry involving solutions. So the 4 steps of stoichiometry, still as in my previous video, are: step 1, write the balanced chemical equation. Step 2, take whatever we know enough about to find the moles and convert it to moles. Step 3, use our mole ratio to find our moles of our unknown. And step 4, convert moles of our unknown to our units desired. So the steps are the same, whether we're talking about gravimetric stoichiometry, gas stoichiometry, or solution stoichiometry. What's different is what we use to do those conversion steps. So when we've got solutions, we have calculations involving concentration and volume as opposed to calculations involving mass and molar mass. So in our example question here, we've got 15.1 milliliters of 0.1 molar magnesium bromide reacting with silver nitrate solution, and we've got the unbalanced equation. So if step 1 is write our balanced chemical equation, that's the first thing we need to do. So if we look at the substances we have there, we have 2 of the nitrate on our product side and only 1 on our reactant side. And we have 2 of the bromine on our reactant side and only 1 on our product side. So to make that work out, we're going to need 2 in front of our 2 silver compounds. And so we have 1 magnesium bromide plus 2 silver nitrate gives us 2 silver bromide and 1 magnesium nitrate. So I always like to take my known values and put them right underneath what I've got in my equation. So when we have that, we can see there's enough information about the magnesium bromide to determine moles, but there's not enough information about anything else. So step 2, convert given amount to moles. The only thing we know enough about to convert to moles is our magnesium bromide. So we're going to take that value, those 2 values I should say, the volume and the moles per liter, and we can either do it by formula, right? Our C equals N over V, we can rearrange to solve for N, or we can do it with dimensional analysis. So I'm going to show it first with dimensional analysis, and then I'll briefly also show the solution using formulas. So our first step, convert that to moles. Remember that capital M stands for moles per liter, so if we're using dimensional analysis, we want our liters to cancel out. So we can change that milliliters to liters and multiply by concentration to get the liters to cancel out. So we end up with 0.015 liters of magnesium bromide times the concentration, and that's going to make our liters cancel our liters. Once we have that, we've done step 2, convert to moles. Now we want step 3, use the mole ratio to find our moles of unknown. So our ratio in this case, our unknown, we're looking for concentration of silver nitrate, and our known is magnesium bromide. So just like we want our units to cancel out in this step, in the next step we want our magnesium bromide to cancel out. So we want magnesium bromide in the denominator and silver nitrate in the numerator. So that becomes a 2-to-1 ratio, and again we can cancel magnesium bromide, magnesium bromide. So if we stopped right now, we'd be at moles of silver nitrate, but we don't want moles of silver nitrate, we want concentration of silver nitrate. So to get to concentration from moles, we need to divide by liters. So this one's a little different because our final units that we want are moles per liter, right? That's concentration. So to get that, we divide by liters. So unlike our other calculations, we're not going to end up canceling any units here because we want the moles to stay, but we want them to be moles divided by liters, so we get moles per liter. So all of this results in our overall calculation. So remember, multiply by 0.1, multiply by 2, divide by 0.01 to get our overall answer. of, sorry, gotta scroll down here, 0.032 molar silver nitrate. So that's how we would do it using dimensional analysis. Now, there's nothing wrong with doing it using formulas. It does end up taking a little more space, and each step gets shown separately, so it's a little bit longer to do it by formula. But I am going to show you just so you can see that both options work, especially if you're more familiar with using formulas. You might like to see the comparison. So step 1, balancing the equation, no difference whatsoever. Step 2, convert to moles. While writing our formula, that's the rearranged concentration formula, C equals N over V. So we plug in our values, we get the moles. Then we do the mole ratio. So the mole ratio is a little different when we're looking at formulas. We set up the proportion unknown to known and identify what those values are, right? And we plug in our unknown, which is silver nitrate, we put as a variable, over our known in this case, is the value we just calculated in the earlier question. And I see I mistyped something here. That should say 5.1. So when we do that, we use cross multiplication to solve for x, and we get 0.003 moles of silver nitrate. Step 4, convert to concentration. So again, we put that back into the concentration formula, C equals N over V. So we take this new moles, divide by our volume of silver nitrate, which was 10 milliliters, so change that to liters. And we end up with the same overall result, which is 0.032 molar silver nitrate. So, right, same answer we got up there. So it doesn't really matter which way you do it, but if you compare this, right, our steps using formulas takes up quite a bit more space than our steps using dimensional analysis. And it's just a little longer to write out because you're writing down all those intermediate steps. And you might make mistakes like I did where I mistook that one intermediate step. So dimensional analysis gives you less opportunity for making those mistakes. Going to do one more example, also using dimensional analysis. So this time we have what volume of nitric acid is needed to neutralize 45 milliliters of KOH solution. So neutralization reaction, acid plus base produces water and salt. So in this case, our salt is going to be potassium nitrate. And remember, we can write water as H2O or HOH. The only reason I tend to write it as HOH in these questions is because it makes that double replacement reaction a little more obvious, and also therefore a little more easier to balance, because now I can look at OH as a group, right? I've got one OH and one OH. I have one hydrogen and one hydrogen, one nitrogen, one nitrate and one nitrate, and one potassium. So I can see, okay, this one is already balanced. So from there, I can identify my knowns and what I'm looking for. So I know concentrations of both of them, and I also know volume of the KOH solution. So I'm looking at calculating the volume of acid. So again, looking at our dimensional analysis, what we get out of that. So first step, which thing do we know enough about? Well, we have volume and concentration of our KOH. So volume times concentration is going to give us moles. Again, convert those milliliters to liters. So let's move this up so I have some space for answers. right? So there's that step 2, convert to moles. Once we're at moles, we want our mole ratio. So in this particular case, it's a 1-to-1 ratio. So that's a pretty straightforward calculation. And then this time we want to know volume. So if we've got concentration, remember these units that are things like grams per mole or moles per liter, we can flip them upside down if we need to. So in this case, looking at what units we have and where we want to be, we've canceled out our liters. We've canceled out KOH. So now we're at moles and we want to be at volume. So we want those moles to cancel out and we want to be left with liters. So we want moles on the bottom, liters on the top to make that work. So we take our concentration, 0.150, that's our moles per, on our other side, 1 liter. So moles on the bottom, liters on the top. We get 1 liter over 0.15 mole. And then we can work out the math. So multiply 0.045 times 0.55, multiply by 1, divide by 1, so we can skip that in our calculators, and then divide by 0.0150 moles, and we get 0.0165 liters of nitric acid. So hopefully those 2 examples help you out a little bit in how we look at solution stoichiometry.